Okay, then let us start as soon as possible. That means immediately. So today our speaker is Artem Sobolev, engineer at LK Inc. Wow, wow, wow. This is mine. And the topic of his talk will be, in some sense, review of stochastic differentiation and stochastic computational graphs. So this topic is extremely important, especially for us, since many of us are dealing with the Bayesian neural networks. That are exactly the examples of stochastic computational graphs. So it is important to know what are the tools which can be used for performing doubly stochastic procedures, right? Such as recurrentization tweak and reinforce. Although it's assumed that almost all of you are familiar with it, and it is always a good time to make some kind of review and to ensure that we all understand the mathematical tools properly.
Thank you for the introduction. Yeah, this is my name. This is the fancy startup I work for. By the way, this is my Twitter and this is my blog. So subscribe, share, follow, like, you know. Okay, let's get started. Yeah.
It's the first time that I see your name in English in this form with.
So subscribe to our YouTube channel. And
well, it's very hard to say to foreign person, to English-speaking persons, how to pronounce my name because there is no sound "ch" in English. And I have yet to discover any plausible way to introduce myself. So this talk will be a little bit different from what we had so far. It will not present any original research, it will not present any of my research, but this is more of an overview, this is more of an educational talk that I would like you to introduce you to modern techniques of dealing with stochasticity in your graphs. Let's get started. So this is an outline of the talk. It's pretty big, I'd say. So in the first, I'd like to introduce you what I mean by the computational graphs, to set up some general notation. I'm pretty sure you all are familiar with that, and it won't take much time, but we needed to just define some basic notations. Then we'll consider the general case, the well-known reinforce estimator. We'll see what it does, and we'll somewhat discuss why it might be why it's bad, why people don't use it that often. This is, well, one can kind of expect that because rarely in computer science there is some silver bullet that will solve all our problems. Most of the time we need to specialize, we need to consider special cases, and that's what we will do. First we'll start with the continuous case of continuous random variables where there is efficient representation tree and its generalizations. And though these will mostly solve the problem for continuous case. Though there are some works to improve these estimators even further. What's hard though is discrete case, because in discrete case there is no inherent notion of differentiability. When the variable is discrete, there is no infinitesimal change when you perturb the parameters. When you change parameters slightly, that does not mean that the random variables themselves will change slightly. So first we'll try to relax discrete variables to approximate them with something continuous. But then we'll get back to the general case of reinforce and try to fix that. Try to fix its problems and see what we can do based on what we will know by that moment. Okay, so let's just move on. What I mean by computational graphs? Well, essentially, in my talk, in my speech, in my notation vocabulary, computational graph is just a neural net. I don't like the term neural networks because it hints on neuroscience, and we know that neural networks are not what our brains do. So why use this unnecessary neuroscience reference when it's actually not correct? Moreover, quite often we might consider some fancy architectures, like this one. Suppose you are doing video classification So what would it be, convolutional neural network or a recurrent one? Well, those are not distinct types, those are just differentiable functions that you can compose. For example, you can apply convolution filters to each frame of each time step of a video and extract some abstract features from that timestamp and then feed those into a recurrent neural network. This will be some kind of conv LSTM. The workhorse of deep learning is, of course, the stochastic gradient descent, and that relies on having an estimate of the gradient of some loss function applied to our architecture. In stochastic computation graphs, what's different is that we introduce these stochastic nodes that are not clear how to work with in case of computing the gradient. When you compute the gradient, the so-called backpropagation, you essentially backpropagate the error from the loss back towards the inputs, but it's not clear how to differentiate how to compute the Jacobian of these random units, and one can expect that it's not even possible for discrete random variables. Why we might want to do so? Well, for example, suppose that you have a dropout and you would like to adjust the dropout rates. You would like to drop out some meaningless features more often, and well, you don't want to drop out very important features at all. So if you want to set up the dropout masks, you will have a parameter guiding your dropout masks, and you would like to do gradient descent with respect to this. Maybe you even want to generate those masks using a neural network. For example, in LSTM, there is just, when we use the gates are just sigmoids multiplied to your vector. But you can actually sample Bernoulli random variables from this and apply kind of hard masking. So this talk will be about the situation when we have some stochasticity inject in our graph, and we would like to obtain gradient estimates with respect to parameters guiding this stochasticity. So in mathematical terms, that becomes the following objective. Suppose, let's forget about the inputs, let's only worry about the stochastic units. With respect to stochastic units, our loss will be just an expectation with respect to that distribution where the samples come from. For example, in case of variational inference that you all are familiar with, this would be just the elbow, the evidence lower bound, and we would like to maximize it in case of VI. In this talk, I assume that there is some f capital of z that would be, for example, a loss function applied to your neural network, and you would like to minimize its expectation where the random samples come from some parameterized distribution. Of course, your function itself can depend on parameters theta, and it will, but we will not worry about differentiating this f capital with respect to theta, because that's actually easy. You can see from this formula that the gradient of this whole expression is the sum of two terms. The first term is the gradient of this distribution, so essentially it measures how much the whole thing is influenced by our choice of distribution pi of z. And the second term is just the expectation of the whole thing, that of the gradient, that measures how the function itself influences it. So the second term is easy to compute. You just sample your random variables as usual and substitute them into the gradient.
Still quite nice notation.
Well, yes.
Everything is correct, but the notation is a bit confusing.
Well, and that's what I came up with. There is a paper called Gradient Estimation Using Stochastic Computation Graphs that basically develops a calculus over this. It tells you if you have some fancy graph with lots of random nodes, it tells you how to traverse this graph and compute the gradient estimates using the reinforced trick, because it's kind of not. When you use the reinforce, you don't backpropagate from through the reinforce. Instead, you kind of multiply the your final loss by some gradient direction, but we'll see that later. Anyhow, this time I don't really think that this is important to know. I guess that can be you can derive those methods, those techniques by yourself by just thinking how the things should work, from what I will tell you. Okay, so a bit of motivation, why you would be even interested in that. There are many papers, especially recent papers, that use essentially stochastic graphs. For example, you can use them to train variational autoencoders. That's a generative model. You can use GANs with discrete data. In case of discrete data, your generator outputs not some continuous objects like images, but discrete data, and you will need to backpropagate your errors from the discriminator through this non-differentiable process that needs some handling. Or you can use this stochasticity for control in deep models. For example, you can use external memory and use these methods for essentially hard attention on this external memory. There is a well-known paper by our group on variational dropout that specifies deep neural networks. That was also obtained using the same ideas. And in reinforcement learning, you can learn a model, a differentiable model of your environment, and backpropagate gradients through that. So, whereas previous examples mostly concerned with variational inference, or could be somewhat kind of based on variational inference, this one is less so. This is a different formulation, I'd say.
So this means that in this case there is no alpha, there's different criterion, but which is still expressed as an expectation of a distribution with respect to whose parameters we would like to optimize.
Right.
Right, the whole criterion. My question is about variational memory addressing. Do you understand right that stochastic computational graph arises there if we are using some analog of hard attention for this memory? And if we are using soft attention for the access to memory, then there's no stochasticity in the graph.
Right.
Right. Good.
Can you clarify, in the last points, do you mean like reinforcement learning in general or some specific form of reinforcement learning?
This is a paper by DeepMind where they learn the differentiable model of an environment, and then essentially maximize expected reward from and backpropagating through dynamics of your environment.
But it also arises when we are using randomized policies, right?
Well,
because we need to take an expectation with respect to
yes,
output.
yes, they do use randomized policy. This is kind of policy gradients on steroids, but you can't apply these methods to policy gradients right away because you don't know in general the reward function, you don't have a differentiable model of reward, and then most importantly you don't have differentiable model of your environment, and that matters a lot.
Right.
Okay, so let's talk about math. The general case, the reinforce, it can be derived quite simply actually. I remind you that we are interested in gradient estimates of our expected loss. If we rewrite the expectation as an integral, that would be this quantity, then we can, assuming some mild condition on the integral, we can exchange the integration and differentiation, then the first term does not depend on theta itself. All the dependence is here in density function. So we put the gradient operator here. Then we note that if you differentiate the logarithm, then it will have this density in the denominator, and in the denominator you will have gradient of pi, this thing. So if you simplify this formula, you will apply this one. So this transition is correct. And here we see that this is just an expectation of a gradient logarithm multiplied by value of your function. If you look closely at it, then the intuition becomes pretty clear. Yeah, and then when you want to actually use this gradient estimator, you just sample z from this distribution and use this quantity as a Monte Carlo approximation. So the intuition is actually pretty easy. First, you can see that the only thing that determines the direction of your gradient is this gradient term, because the f of z is a scalar. So what this gradient estimator says is that you should go you should maximize the probability of log probability of quantity of sample z, and these directions are weighted by the value of your function for this sample. So you maximize probabilities of those samples that lead to big values of f. However, there is a problem with that, because, well, first you would expect that knowing gradient information about f would be helpful, and indeed, even from what I said, it's clear that if your f's are all positive, that means that every direction will have positive weight. So the only way to penalize bad directions, bad samples, is to sample better ones. That means all directions will have some positive weight. Directions to optimize all, to maximize probability of every sample will have positive weight, but well, yeah. So it only pushes the probability of good samples, but its behavior is not nice when your f is only positive or only negative.
Artem, and what happens if f is always negative? Does it mean that we will always go to the opposite directions?
Yes,
So
we will always go to the opposite directions, but
Does it make sense?
well, the thing is that this quantity is your gradient direction only when you average an infinite amount of samples. So that means that you will go towards the really bad samples with a greater magnitude. Really bad samples will have a bigger weight. So when you renormalize it, when you get your probabilities back, that would mean that for good samples, you will decrease their probability only slightly, and for bad samples, you will decrease their probabilities a lot. So when you renormalize it after, the bad samples will decrease. Well,
But this is, I understand that mathematically this is correct, but this is still sounds strange.
no, it's
We
not.
always go into the opposite directions, but in the case of bad samples, we go to the opposite direction far away, while in
Right.
the case of good samples, we're almost on the same place, in the same
Right.
position. But we're not going to the right directions,
Yes, we're not. But when you
and we're still optimizing the criteria.
right, that's actually the source of high variance that this estimator is known for.
Right. One of
Yeah,
possible
because-
explanations.
Because in order to compensate this bad direction, in order to compensate for this negative weight for even good directions, you need to have some bad directions that would take most of its mass on itself.
actually didn't get it. Like, why do you think that always, like, say it's always positive, right? In this case, why it's bad? Like, what's wrong?
It's bad because positive samples. Suppose you have pretty bad pi that puts a lot of weight on samples that lead to poor value of f. Then you will be if you just use just one sample and that sample is bad, then you will go on direction that maximizes this sample's probability. It will have a little small weight, but still you would make some small step towards that action, towards that sample.
Okay.
And it works because when you average a lot of these samples, the good samples will have higher weight, so you will optimize harder towards them. And when you consider probabilities, these good samples will, in the end, have a higher mass.
Okay.
For them.
So you think that it will be better to maximize the probabilities of good samples and minimize the probabilities of bad samples?
Yeah.
Okay. I see.
That's also actually why people subtract baselines from f, so that the f is not strictly positive or strictly negative. Okay, so it's very general and doesn't need to know how to differentiate your f. However, people reported large and unpractical variance of these estimators, and people don't use it in this formulation. Instead, they apply some different variance reduction techniques that we'll talk about later. And for now, we'll discuss continuous case, where we can actually backpropagate through random nodes, and I'll tell you right now how to actually compute the Jacobian of a random variable. Yeah, you can do backpropagation through randomness, and as a result, you'll get random Jacobian. The idea is based on the following observation that if you have some random variable x theta, x that depends on some parameter theta, and you pass it through its cumulative distribution function, then what you'll get is a uniform random variable on the interval 0 to 1. And what's interesting is that the result does not depend on theta at all in any way. So the CDF kind of whitens all the dependency out of your sample. So if we differentiate this thing, essentially what it says is that the gradient of this thing with respect to theta equals to 0, because the right side, the uniform sample, does not depend on theta at all. Then, by just using some rules of calculus, we write the gradient of a composite function as sum of two. First is the gradient of your CDF with respect to theta, and the second is your density at the given sample times the gradient of sample with respect to theta, what we're actually looking for. If you rearrange the terms, well, these two things sum to 0. So what you get is that the gradient of your sample is proportional to the gradient of the CDF with respect to theta, and it has a negative weight of 1 over density.
How did you get this decomposition? How did you derive it?
Okay, let's derive it on the whiteboard. Suppose we have some x that comes from the distribution pi of x, and its CDF is f of x. Then it's known that if we compute, okay, let's change the notation. Wow. Let the variable be this way. So if you compute the CDF of Xi, that will be distributed identically to some random variable that's uniformly distributed in 0, 1. Then we differentiate both sides with respect to theta. And the right side is obviously 0. The left side, though, has dependence on theta in two places. First, the sample itself depends on theta, and then the CDF depends on theta. So, first you have the partial derivative of your CDF.
So this is the differentiation of an integral whose limit is also dependent on the variable with respect to which we differentiate.
Yeah, yeah.
And so we're doing just according to the known theorem from calculus, right? So this is exactly what I wanted you to explain.
Well, yeah.
We need to differentiate subintegral function, and we need to differentiate the upper limit itself with respect to theta. And this is what Artem is doing.
And just rearranging terms of this equation, you can obtain the following formula. I'd say it's actually less intuitive, and by thinking some amount of time, I couldn't come up with an explanation why the formula is like this. So if you have and if you understand why it looks this way, like we just saw for the reinforce, we saw that it just maximizes probability of a given sample. So I'm not sure I understand what this thing does. It looks like again, as a direction, it just uses the direction that maximizes the CDF of your sample with respect to theta, but then it reverses that direction and divides it by the density, and that's less intuitive to me. Anyway, this is a nice mathematical trick that is not widely known, I'd say. I haven't seen anyone using that, except, of course, for the paper where I originally read about
Well, it was presented just this year.
No.
Okay,
Alex
and
Grace presented it last summer, in his paper about stochastic propagation in density mixture network, something like this. That was more than a year ago. Several deadlines.
There are a few people who understand it, who really understand this trick.
This trick was in the first or second page, and I'd say it's actually very easy to comprehend. I'm not sure whether it actually gives you that much power, because you need to be able to differentiate from CDF, and I guess for most distributions that we want to do so, there are already known reparameterizations, like for Gaussian distribution.
Right.
If you do this for Gaussian distribution, I kind of checked that, and it looks like it will lead you to the representation trick, the well-known representation trick, so no mystery here. So the representation trick. What people did before this thing was invented, was presented, and what they still do is use Gaussian random nodes, Gaussian latent variables, and if you have some Gaussian random variable z that distributed with some given mean and variance, that the following can be noticed, is that this random variable has the same distribution as the following. You can sample some independent random noise, scale it by the square root of your covariance. This is the matrix square root, not pointwise. And then just shift it by the mean. Then your stochastic computation graphs becomes this one, and you no longer need even to backpropagate through stochasticity. Your stochasticity comes from above. In mathematical terms, in general, that means that if you have some way to construct the random variable of interest, the z given theta, from some independent noise epsilon, using the transformation that sort of bakes those parameters into the sample, then you can rewrite your function and the gradient accordingly, like this. So when you rewrite your function by sampling the independent noise epsilon, you no longer need to differentiate with respect to your distribution, with respect to the random variable to the distribution you take the expectation over. So you only need to, when you differentiate this thing, you can just pass the gradient operator through the exchange the differentiation and the integration, the expectation, and get this formula. And that can be efficiently computed using the backpropagation, standard backpropagation. In practice, this is a very efficient estimator. However, it's not as general as we might want it to be. For some interesting distributions, like the Dirichlet distribution, there is no known representation like this one. Well, sometimes we might want to work with these distributions also. So that's...
So actually, the criteria is pretty simple. If we have constructive algorithm which allows us to generate the given distribution from a, say, uniform distribution from 0 to 1, then it's okay. Then the representation trick is applicable. If not, then we're in trouble.
Yeah, unless you know about the generalized representation trick.
Right.
And the idea is the following. Okay, so we cannot come up with some random variable epsilon that would that you can map onto a random variable that you're interested in. So, but what this is doing is that, okay, suppose that t is invertible. Then the inverse of t can actually take your random variable and remove all the dependence on theta completely. You'll get epsilon, that is just a white noise that is completely independent of parameters theta. Just like we had here, the CDF was this whitening function that was completely removing all the dependency on theta from our sample. So, okay, if we cannot come up with this, maybe we can just whiten your, maybe we can remove just a bit of dependency. If we cannot remove all of it, let's just make it like zero mean and unit variance, so that the first two moments are independent of your parameters. Or you can whiten even more moments if you can do so efficiently. And usually you can compute these moments analytically because you know your distribution. For example, for Dirichlet distribution, you know what its mean and its variance are. So it's not hard for you to compute this quantity. Just just whiten the first two moments. Then, if you write the gradient, it actually becomes sum of two terms, because now you can just forget about gradient with respect to your random sample. So at first it looks like there is no use, because there is still this gradient of this like reinforced looks like reinforce like gradient. However, there is still some signal coming from the reparameterized version. So what first way to see this formula is that this thing does this thing uses reparameterized version, and then it corrects for the bias. Because if you remove the second term, of course you will have biased gradient that will optimize something different. But then this thing corrects for the bias, and hopefully if there is a reason to assume that you removed most of the dependency, that the higher moments doesn't really matter, then this term is not really influenceable. You can hope that the disadvantage that the minuses of reinforce will not hurt you, will not bite you.
So the signal to noise ratio will be still low, but the magnitude itself of this stochastic term, second term, will be more or less small in comparison with the first term. This is our motivation.
And actually, there was another paper by authors of this paper, the generalized reparameterization tree, where they showed that this technique can actually be seen from the rejection sampling perspective. Then you don't need, well, here
those two are different, unfortunately. There is no way to link them directly.
I don't think so, but we can discuss it afterwards.
In the cinema?
Huh?
In the cinema?
In the chat. So what it says that so far we assume that we can compute both the transformation and its inverse, but and we will assume that because we don't want to sample from epsilon, though it's not that hard actually. You can sample that as usual and then just apply the inverse. But if you can sample them straight away, then you don't need this inverse, and this transformation can be, well, non-invertible, because, well, that's vegetable transformation. Anyhow, okay, let's not dig into that because I don't want to cover that right now. So if you rewrite this formula and get rid of from epsilons, because you don't really want to, well, maybe you don't want to sample them. If you want to see what the formula for the gradient looks like in terms of your real samples, in terms of your real random variables Z, then it looks like this. And again, this can be seen as a combination of reparameterized gradient and the score function gradient. But here, what's interesting is that it's not just usual. It's not usual reinforced gradient, but it has some control variate in it. It has unusual control variate because usually we subtract baseline from the function itself and leave the gradient direction the standard. And here we modify the gradient direction.
What is the, you have two lines?
Yeah, and the gradient is just the sum of them. First,
Where is the plus?
it didn't fit. There's no place for this plus, sorry.
Ah, so this is...
But there should be.
You should write like first line plus, and then the next line, and
Right.
fit.
Otherwise, it's very misleading. So actually, what did we do? Can you generate it on the whiteboard?
Can we have a bit of help?
Yeah.
I
Because
don't want
usually
to
the
because it's just no, it's pretty easy. You just need to write the density of your random sample.
You're welcome.
No, okay, we don't have enough time. We don't, I assure you. It's already 7:30. This is not so important after all.
Okay, what is the conclusion?
The conclusion is that the generalized parameterization allows you to interpolate between reinforce and reinforce and reparameterization, because if you have a really good transformation T that removes all the dependency completely, then you can see well, I guess from this formula that okay, you can see from this formula.
What is the difference between this and traditional baseline techniques?
The difference, as I said, is that we don't subtract from the f, but
Right.
we rather add some different direction.
Can you repeat this? Where is the part from reinforce and where is the part from something else? Because I can't see
first
anything
the-
from these.
Okay, see here in the first term we have the derivative with respect to z. This is something you don't have in reinforce. In reinforce does not use gradient information of your objective at all.
Right.
And that's what you see in the second term. This is reinforce, and
The first
first
one
is
is
reparameterization. Right?
Yes.
And
Second is reinforce. But why do you tell that there is some specific baselines? Isn't it something that is done in reinforce as well, or not?
I haven't seen that. I haven't seen anyone modifying the direction itself. I only seen people modifying this scalar value. Yeah.
Does it connect it with Q-prop somehow?
I haven't read that paper, sorry.
And with rebar?
No.
No. I still can't understand why the expectation is 0 of this baseline. Can you give some intuition?
I don't think their expectation is 0. It's definitely not. It's actually this term. Oh, no, okay, not.
No, the expectation of the baseline.
Yeah. If you if you remove these terms,
Right.
you will have the usual reinforce.
Right.
But the total gradient is actually sum of these two terms. So that means that actually expectation of these two terms times the f is minus this guy.
Mm-hmm. Mm-hmm.
And that's actually interesting because I believe, I thought that it could lead us to better baselines for discrete problems, but well, at least from 2 minutes thinking, I couldn't come up with anything.
This is why
But at least
I was
it
asking
might
you
be, it
to
might be
make this a
progress.
bit of algebra on the whiteboard, in order us to understand better.
Okay, let's better do the algebra of rebar in the end.
Okay.
Okay.
Another bit of algebra.
That's actually pretty simple. That's very simple. Don't look at the formulas so far. Just okay. Let's consider a very simple example of optimizing the following objective.
you can see the formal.
You have,
Everything on
you have random variable that is normally distributed with a given mean and variance, and you want to optimize over this variance. You want to minimize this expectation, and the C is just some parameter, free parameter that obviously does not affect the optimization at all, but it will, as we will see. So you can rewrite this this objective using the reparameterization. And then let's see how the gradients for two estimation schemes, for the reparameterization and for the square function, also known as reinforce, behave. Even from the gradient estimates themselves, you can see that reparameterized gradients look nice, and the reinforced gradients have this sigma in the denominator. That actually means that as you and the optimum of this function is obviously for mean and zero, and for mean and variance being 0. So as you approach the optimum of this function, that means that your gradients will explode by magnitude, and this will be especially noticeable if your denominator is not 0, and it will not be 0 if you have c greater than 0. That's why I introduced this parameter. And the variance formulas actually confirm that the variance explodes for reinforce if your C is not 0 and you approach the optimum. So
you're saying that adding constant to the to f may help, right?
No. The adding constant to f can actually break your reinforce. It can explode your variance and
Well,
it
and
won't
vice versa,
converge.
if it was like, I mean,
Yeah, of course. If it was already biased and then centering it, making it like 0 at the optimum can help. I'm not sure about the general case though. Okay, so here are some plots. First for c equals 0. This is the loss for various iterations. You barely see, well, it's the only difference that can be seen is that there is much more variance in score function rather than in reparameterization. The reparameterization can barely be seen. If you look at the plots for values, for mu and sigma, then kind of the same. Both methods converge, but it looks like the score function has more variance in it. For sigma, actually reinforced converges slightly faster, but well, no big deal, both methods still converge in the end. However, if we increase c to 1, you can see that the reinforced breaks and it stops converging. It just oscillates.
I wonder, what happens if c is negative?
Well,
I'm not sure.
not actually, because in the if
The
you look
expression for the variance?
right, if you look for the variance, it will be minimized here. Actually, it's interesting to minimize this expression with respect to c, and well, I guess that will lead you to the optimal baseline for reinforce.
Right.
of
But I
inference.
thought you have a problem with the first term.
Yes,
no?
it's square term. But anyway, there should be somewhere optimal with respect to c.
Yeah, but still, I don't think it will help you with the variance because this thing is always positive.
Yeah,
Yes.
and it's a bit a lot.
Wait, is it the same, exactly the same as baseline or something else?
Yeah.
What?
This C term.
Well, here I don't adjust it. It's just a hyperparameter.
Yeah, but
Well, it's not a hyperparameter. It's just some parameter of your problem. If you learn it, then it will be a baseline or.
No, it is always baseline. It's not necessarily a good baseline.
Well, okay. If you.
It doesn't change the position of our minimum, right?
Yeah.
But we may vary it, and depending on the particular value of C, we may get different stochastic optimization algorithms with different variances. That's quite interesting. But this is, again, the same motivation as for the baseline, actually.
Yeah, this just demonstrates the need for the baseline for reinforce because it doesn't converge at all.
And if you remember this paper by ours, relation of the powers specified neural networks, there we also had a quite similar problem. So we could not optimize the criterion because of high variances of stochastic gradients until we changed, but in our case it was not baseline, it was parameterization. Until we switched to different parameterization in which stochastic gradients became very low variance. And we were able to optimize it finally. So this is quite an important problem. And it arises in many different areas.
Okay, let's move on to discrete relaxations finally. First, I'd like to talk about what I call asymptotic reparameterization. I have not seen anyone in any paper mentioning that, though actually this is what sort of justifies using rational dropout. Why using Gaussian dropout can be somewhat justified as a replacement for binary dropout. And the idea is simple. Suppose you have a binary dropout, then what that means is that you have some mask of binary random variables, and at some point then you will have them, for example, suppose that nodes of a given layer first masked, then you apply the weights, then you apply activation function to these weights. That means that the pre-activations of this activation function, the random variable, the nodes of a given layer after linear transformation by the weight matrix, is just a combination of many independent random variables, well, with some weights, but they as independent, and we can kind of hope that the central limit theorem holds. At least asymptotically as you increase number of units in your layer. Yeah.
I didn't get the peak in the last line.
Okay. Let me draw something then. Suppose that these are your nodes of a neural network. They are somehow computed. And then you apply binary mask to each neuron. And then you just linearly transform them using the weight matrix, apply weight matrix. What you get is that, okay, so this is X, no, this is H. We multiply H pointwise by mask Z. Then we apply the weight matrix and probably bias, but it doesn't really matter. So what this thing is just a sum of bunch of random variables, this one, that are somehow transformed. So one can cross their fingers and hope that the CLC holds, and this thing is approximately normal.
Why only with hope?
Well, because we have finite amount of nodes in
But like
Z.
central group theorem doesn't like it's beholds, no?
It's asymptotic result.
No, of course. But wait. Okay.
Well, it approximately holds, but then again, it has this requirement that no random variable dominates others, and I guess that can be violated by the weights. Anyhow, if we believe that this quantity is approximately normal, then we can replace these binary random variables with normal random variables that will preserve moments of this pre-activation. So then, when you replace discrete random variables with continuous ones, what you will have in the limit, all the random variables will have the same distribution, and so you can replace the one expectation with respect to expectation with respect to discrete random variables with expectation with over continuous random variables, and nothing would change, but in the limit.
Well, this can be regarded as one justification of Gaussian dropout.
Right.
And
it allows you to replace your binary, your discrete random variables by continuous ones, for which we already know there is a reparameterization trick.
yes, but this is some kind of ad hoc trick.
Right. It's very limited. It has very limited applicability scope. It heavily depends on your ability to invoke some kind of concentration, some kind of
limit theorems.
yeah.
Let's be honest.
However, I could use that for discrete variation autoencoders, so that's already something.
You could?
Yeah.
I mean, you did?
Yeah. But
We
I'll
can
show you
discuss
some.
it in details.
I'll show you some plots later. I have plots for this method also. So yeah, the benefits is that we can justify it somehow if we believe in central limit theorem, and that gives you all the benefits of Gaussian reparameterization, but it has very limited applicability scope, and depends on how good the CLC approximation is. If you have just 5 neurons in your hidden layer, then it's very unlikely that they can be replaced by Gaussian units.
And the idea here is that you will use continuous random variables while training and then discrete random variables.
Yeah. The idea here everywhere is that we use some kind of reparameterization, relaxation, something during the training, and use discrete random variables at testing stage.
And what's the motivation?
Well, for example, you would like to have sparse samples, that only select some weights or the application I like to think of is we might want to train like an ensemble of many methods. Some methods are easy and quite quick and fast to use, but some methods are hard and low and slow. For example, for classification, you can use some small neural networks that can process simple inputs fairly quickly, and some large monster like 1,000 layers deep ResNet. And then you could have some manager that selects one of these models based on some features of your input. And if you use a weighted combination of all of them, you can't save any time on preceding this image. However, if you use sparse samples, you can.
Yeah, okay, good.
Okay, another idea is the following. So let's think how we even get the Bernoulli samples, the discrete samples, and maybe we can come up with some, maybe we can relax this sampling and backpropagate the rate. Well, if you want to sample a Bernoulli random variable, what you can do is to take any continuous, well, okay, any distribution at all, it continues on some support distribution. Take a look at its CDF. We know already that. Well, okay. If you take some level p, then we know that the amount of probability here is exactly p, and in the rest it's 1 minus p. So what we can do is to see whether our random sample ends up here, like sample some random variable from this distribution with this CDF, and see whether it ends up here, then it will be 0, or it ends up on the right, then it will be 1. This is what the formula. The first formula captures. It just compares your x with the quantile of your distribution. The h is a step function, the so-called Heaviside function. That's just one, just 0 for negative values and 1 for positive ones. And it's undefined for 0, but we don't care. So obviously this function is not differentiable. What we'll do then is that we replace this step function with a sigmoid, and the sigmoid with the temperature. What we want to approximate is this function. But we know that there is like continuous function that looks like this, the sigmoid, and if we multiply the argument of a sigmoid by some scaling function, that would influence the steepness of this function, of the sigmoid. So by controlling the scaling factor, you can make sigmoid look more like a step function. Actually, in the limit of infinite scaling factor, you will recover precisely the step function h. That's what this formula says. Okay, so this is actually pretty general, and when I was preparing to this talk, I couldn't actually come up with a good idea of, with a good explanation why the choice of x should be the one leading to Gumbel-Max relaxation. What I came up with is the following.
Sorry, repeat again. What was unclear?
Well, you see, this derivation works for any continuous random variable. How do we choose specific ones? Some are probably better than others.
You mean initial continuous random variable?
Yeah.
Oh, but for the binary case, it works for any of them.
Right.
And for the categorical, for the non-binary case,
you have to construct some strict break-in apparently. That's actually my motivation for the Gumbel softmax, is that that's the only, at least known for me, scheme that is general enough to, that is naturally general for multivariate case, for categorical case, and it has some specific special case in binary, for binary random variables.
Yes, but for binary random variables, any continuous distribution will do.
Yes.
For categorical, just Gumbel softmax.
Well, you could construct some kind of stick breaking process, but I guess it won't be easy and probably won't be comfortable to work with.
And I don't think that there is any reason for construction. We already have Gumbel distribution, and we're okay with it.
Well, it does not sound as a mathematical principle that will say that you should only use Gumbel softmax and nothing else. Okay, so the other idea is that we would definitely want our support. Well, another point to notice is that we would actually want our distribution, okay, so what we do in this scheme is that we sample some x from some continuous x from continuous distribution, and then use the following relaxation, where theta is the hyperparameter controlling how good our our relaxation is.
So if tau is 0, this will be Heaviside function, and this will mean that with the probability of alpha, it will return 0, and the probability of 1 minus alpha, it will return 1, right?
Yeah.
So we managed to get our discrete random variable from continuous one. The problem is that Heaviside function is not differentiable. So now what we would like to obtain is to obtain some differentiable function, which in some sense is continuous relaxation of our binary discrete random variable. I'm explaining to the audience, not to Artem. Artem understands this. Because this is all very important trick, and quite popular one and quite promising one. So you need to understand the motivation and the intuition behind it.
So another point to think about is that this is another random variable, and this is what we will be using instead of our discrete variables. What we would like this random variable to do is to be close to 0 and 1 as often as possible, because that's actually what our Bernoulli discrete random variables are. If your if distribution of this function has its mode somewhere between 1 and 0, like if it's unimodal, then most of the time this distribution will take some intermediate values that are
May I just try to explain a bit better what you want to see? So, suppose that this is our alpha, right? So ideally we would like to have this Heaviside function. So we sample from what? Actually, why does it matter? Why does it the choice of x matters? After we perform the inverse CDF,
for example, if your x does not have full support, if it has only some subset of R as its support, then you will never sample ones and zeros. You will have zero mass in some vicinity of 1 and 0.
okay, so you want to say something that you replace this Heaviside function with such, say, step function, and if our distribution is, for example, as some kind of such density, right? Then our x minus alpha divided by tau we will have this shape instead of this one which we would like to obtain.
Well, actually, from my experiments, what I've seen is that it will have this shape, but it will drop to 0 before it would reach 1 or 0.
Well, if our base is limited,
Yeah,
it will never reach
yeah,
0
exactly.
and 1.
So that's why first you need full support,
Right.
and then I believe the shape of
And well, large variance or equivalently small tau.
yeah.
So the tip of this sigmoid function should be
Yeah. I mean, the limit holds for any distribution. So no matter which distribution you use, even the one with some restricted support, in the limit any distribution will do. However, in practice, in some non-limited cases, it matters.
Well, obviously, if you have like not exactly limited support, but if one side is much more probable than the other one, then you cannot like fix it with finite tau, right?
Yeah, but why is it a problem? We don't care whether your distribution is symmetric or not. All we care is are its quantiles. I don't think that symmetricity of your distribution is important. Does that make sense?
I don't know.
So why do you think?
Well, let's say you have like with probability epsilon, you will go to the negative part, and you will sample from a Gaussian, from negative Gaussian, right? Like from negative part of the Gaussian.
Mhm.
And for probability 1 minus epsilon, you will sample from the positive side part of the Gaussian. Right? Will we have problems like that? It's like not having full support most of the time.
Okay, can you repeat what the density looks like?
So with probability epsilon, you sample Gaussian from negative part of the Gaussian. So basically, you sample Gaussian until you get a negative number.
Okay.
And
Well,
here-
Gaussian with what mean and variance.
0 and 1.
Okay.
And then with probability 1 minus epsilon, you sample until you get a positive number, and you keep that. Maybe it's not.
Okay, I get what you're asking, but I don't think there would be a problem still. Because all you care about is whether x is greater or not than this threshold. So you will not compare with the mean of this distribution, but you will compare to the quantile, to a given quantile 1 minus p quantile of the distribution. And as long as you can write it down for the distribution that would be generated by your sampling scheme, that's okay.
Okay, I'll think about it.
Then why do we need modes in 1 and 0?
Because at the test time we'll be using ones and zeros, and we want our training to be close to the test time, because if most of the time you have some intermediate values like 0.3, 0.4, 0.6, then your network will adjust to these values and might perform poorly on the test time. That's why you actually want to have modes on 0 and 1.
You mean in test time we will enable the Bernoulli variable?
Yeah, yeah.
Okay.
So we'd like to obtain continuous random variable, which is as close to discrete random variable as possible. And this is one more constructive way of doing so.
Okay, so this was our desiderata, but the ideas, but what we discussed so far didn't specify which particular x we should use. And as I said, I don't know any guiding principles that would say to you that this is the distribution you should use as x. So instead, I'll say that there is the same trick for categorical case when you have more than 2 outcomes. And because it's more general, you should also use it in the binary case, as it's just a special case of a general technique. And This technique is based on so-called Gumbel-Max trick that specifies how you can sample any random variable by optimizing something. In particular, the Gumbel-Max trick says that if you take a bunch of Gumbel independent random variables, and it doesn't really matter what Gumbel random variables are, they are quite simple to sample. You just need to sample uniform random variable and apply logarithm twice, and well, add minuses where it's necessary to. The Gumbel-Max trick says that if you take these Gumbel random variables and perturb each by adding log probability, then the probability that kth perturbed Gumbel will be the maximal one is proportional to this perturbation. So then, what this formula means is that if you take your Gumbels, add these log probabilities to each of them, and then compute argmax, then it will be distributed as if you sampled categorical random variable these probabilities. If you represent your k, your index of argmax, as a one hot random variable, that would be just a vector where there is only one 1, and all other components are 0. This is a zero temperature approximation of a softmax, the same as before. In the binary case, the Heaviside function, the step function, was a zero temperature case of a temperatures of a sigmoid with the temperature, and here argmax, one hot argmax, is a zero temperature version of a softmax with the temperature. So what this scheme proposes is to just replace your categorical random variables, which whole sampling process can be expressed like this. This is actually a reparameterization for the categorical random variables, but it's not differentiable because argmax is not differentiable. But if we replace it with a softmax, it will become 1.
And so the idea here is we could do the same thing with reinforce, but it will have higher variables, right?
What do you mean with reinforce? How would you do that?
I don't know. I'm just trying to place what.
I mean, we will combine this trick with the reinforce as a very cool baseline in the end. That's what Rebar paper is about.
Okay.
So that's actually a pretty interesting trick, I'd say. By controlling the temperature, you can control the accuracy of your approximation. And that seems the hot technique nowadays.
And it really works. What's interesting.
Yeah, works pretty well. However, there are still problems to it. It's still biased. It's biased gradient. It does not optimize what you will be using at the test time. And so far, all the relaxations we're talking about are relaxations because they will be biased compared to what you'll be using at the test time. And it has this temperature parameter that it's not clear whether you should anneal that or not. Some people report that they can successfully train their models with temperature fixed, as I'd say 0.4. But some people do anneal them, and if you do anneal them, that becomes harder because you need to come up with a schedule to decrease the temperature. And I'm afraid if you increase the temperature too aggressively, you can actually run into the step function, and your gradients will explode.
But still,
Yeah.
like if you have a stochastic computational graph with discrete random variable, you can apply reinforce to it, right?
Mm-hmm.
But this is like this is essentially the same problem, but with different variants, or not?
With different what?
Variants, like
Well, what's cool about this thing is that because you can reparameterize your stochastic computation graph,
Right.
you can actually backpropagate through all the randomness, because the random nodes are not discrete anymore, they are continuous, and you can differentiate continuous random variables. So what you'll end up with is you will be using the gradient information of your objective of f
Yeah.
capital, whereas in reinforce you don't.
But still, both methods like are trying to solve the same problem, but just differently, right? How to like train a stochastic computational graph with discrete random variables.
Well, yeah.
Okay.
Well, this actually just tells you how you can re-express your graph, and it does not tell you anything in particular what you should be doing with your gradients. It just says that if you take your discrete random graph, replace discreteness with this reparameterization, you will have another random graph that, by tuning tau, you can approximate to the original one. So you can hope that if you optimize the relaxed graph, it will also lead to better performance on the unrelaxed one.
What are the problems in practice with biased gradient in this case? I mean, what is the result of the biased
People don't do anything with it, assuming that if tau is like decently small, so that the distribution, so that the those random variables have modes on the edges, on the not edges,
Given one. Like,
well,
given one, like,
well, like on the vertices
yeah.
of the simplex. Then that's enough. That's just some approximation to what you really want to optimize.
One more question about temperature. Why do we need to anneal it at all?
Well, we might be, we not, but it's not clear whether you need or not. Obviously, you have good approximation only in the limiting case, and I don't know. Some people successfully train these models using non-zero and non-annealed fixed temperature. So I guess that's the first thing to try, and then if you run into some problems, then maybe try some schedule.
Yeah, I mean, we just take small enough in this case.
What are the problems in this case? Like,
The problem is that it's not clear how do you even choose the schedule. Like degrees.
You said that like you first try to do a fixed tau and then you try plugin tau, and like then you try fixed tau. You have some problems with it. Which one? Like, what do you see?
Well, I'm not sure what you'll be seeing, but I don't know. Maybe you can. You look at your loss on the relaxed version and compare it to unrelaxed version, to original discrete one, and you clearly see that the relaxed version successfully trains, whereas on the discrete version the loss goes up.
So like in practice, your relaxed version will be not near the edges of the simplex, the vertices of the simplex.
Yeah.
It will be like you will have probabilities in the between the layers.
Now, there are also some other methods that do completely crazy stuff. For example, well, this section is about methods that only relax gradients, that only relax the backward pass. So far we were relaxing the model itself, so that you first compute forward pass in your relaxed model, you obtain error in your relaxed model, and then you backpropagate the error back in your relaxed model. Here people do different thing. They compute forward pass in discrete model, obtain errors, and then backpropagate these errors of discrete model through some relaxations. And sometimes these relaxations are crazy.
Like linear one.
Yeah, like the straight through estimator is completely mind-blowing. It just gets rid of the nonlinearity and the step function and just backpropagates through, like here. Suppose that your P was generated by a neural network that somewhere in the neural network you have a node that decides, okay, that outputs a probability pi of some following node being activated. Like in LSTM, there is a mask for gates. If you were to sample these masks, you would replace the LSTM, the gates, with their Bernoulli random variables.
By the way, does anybody do that?
Yes, and using this straight-through estimator,
And
where
then-
people do crazy thing. Oh, well, they say that, okay, you don't know really how to backpropagate through this discrete node. So what you do is to pretend that these guys don't even exist here. So you pass the gradient like if the graph was this one.
Artem, did you saw like papers about like when people do this with gates in LSTM?
Michael sent this to me, but I haven't read it closely.
When you
okay,
like
well,
sent it
let-
to the
Let
chat,
me just
I didn't see this.
give one comment. So, straight-through relaxation is definitely wrong in the sense that it provides biased gradients. Nevertheless, people have used it very, very successfully because this is the standard way right now to train neural networks which have binary activation.
Wait, are you talking about Benjos or Raikos?
Raikos, I guess.
Well, okay, Raikos is more or less justified, but
okay,
the
they are
original
both
one...
completely crazy in the sense that these gradients are just not correct. Okay, so I'm just saying that despite the fact that these gradients are not correct, they allow you to train pretty big and complex neural networks with properties we cannot yet achieve with other methods, like big convolutional networks which have binary activations, for example. So there is at least some merit in these methods.
Okay, that's one side to the problem, and I believe that you should never use these methods.
But like, what do you think about the fact that they work?
Like these, they are mathematically unsound. Don't ever do this.
But they works.
I don't think so. It's just they only work
What do you
because
think? You don't think so?
they only work because people don't know how to use these more advanced methods, like the Gumbel Max. I believe we will see better performance of Gumbel Max based methods or rebar methods. I believe these are the future.
They used straight-through estimator in Google Softmax paper.
Yeah. That's actually what I have here. Well, they didn't use it. They proposed the straight-through version of Gumbelization, and it actually makes more sense than the original one. You can actually, what makes slightly, well, like some sense in between, is preserving this sigmoid function, essentially backpropagating through mean field version of your neural networks, where each random variable replaced with its mean. And this is again not very good thing to do, maybe, but well, less mathematically scary.
Wait, why? What do you mean by mean field version? And
I mean, well, mean field in the sense that it's mean, and field is just because that's an actual big graph in between.
okay, so it's not like mean
Yeah,
field.
it's not related to mean field in VI, just some people call it this way, and I don't know why,
Okay.
but I just did the same thing. Okay, the one pro I can see for this scheme is that you don't care about mathematics, so you can do anything at all. What you're doing is already mathematically wrong. So, for example, that's the only method that allows you to recall the model that I described previously. A manager that has several workers that. Some of them are simple and quick models, and some are hard, complicated, and heavy. And the manager decides which one to give a task. Like there can be some small neural network that classifies images quickly, and some 1,000 layers deep ResNet that's very slow. So if you use Gumbel Softmax, then you can, at the training stage, evaluate only one model. Because you forget about mathematics and do things that mathematics does not allow you to.
You mean Google Softmax or straight-through estimator?
I mean, in any of these, you can only backpropagate through, well, I mean, you cannot, from the mathematical point of view, backpropagate only through activated sample. But since you already forgot about mathematics here, you can do anything you want.
Wait, what?
I mean, your method is already mathematically broken, so it doesn't matter whether you broke it more or not.
I did not understand the analogy with the manager and workers.
Well, that was the model I was talking about. Like, suppose you want to save time, you don't want to process all the inputs using the same complicated model. What
So you will use sometimes straight-through estimator, right? Like crossing fingers.
Like no. What you can use many methods, but the problem is that with almost all of these, you will have to evaluate all the models on the train stage.
Even with reinforce?
Well, maybe with reinforce you don't need to. No, I guess with reinforce. Well, yeah, maybe with reinforce you don't need to. But with the other relaxations you have to. And in order to don't evaluate all the models in relaxation, you have to deny math. And this is the only method that already does that for you.
I would like to add to that another thing, mathematical thing you can deny is just remove the stochasticity, because in these papers where they train binary neural networks, what they do, they don't sample anything. They actually use deterministic activations. So essentially just apply the step function to the probability. Okay?
Yeah.
And then you backpropagate as if there was no step function. And surprisingly it works. So I think there is something behind that that allows it to work. You just need to figure it out.
May like any of you comment on the fact that like you say that it's mathematically incorrect, but it works. So
It doesn't work
why
well.
why do you think the boom result will work better than this? Not from mathematical point of view, but from like some example.
Okay, so you see, when something doesn't work, it doesn't mean that it will break straight away. It can be somewhat working.
It will break
But,
at a very unexpected moment of time.
I mean, it depends on.
And will fail the whole scheme.
Do you can you come up with some example where like you see like this thing will not work, and the Google softmax will work?
I can't come up with this right away, but later I have a plot where you can see that straight-through estimator, like the ripest straight-through estimator that essentially backpropagates through mean, performs poorly compared to Google softmax relaxation.
And later will be
The last one actually kind of okay, especially if you anneal the
Artem, I suggest to stop here and to continue next week. Because the talk is extremely important. I would like everybody, well, most of you to understand it. There are several issues to discuss, and you're running out of time because...
Okay, let's consider an example. I just want to show you how these methods work in discrete.
Aren't you afraid of being late to the movie?
We have
Let's
40 minutes before
choose
the...
where to stop.
40? I
Yeah.
thought it's 1:30.
No.
No, it's 21:05.
Ah, good.
So, yeah, actually we have just like 10 slides left. So. Okay, let's consider an example. All you know about the usual variational autoencoder, but let's consider a discrete one because, I don't know, for some reason we want to have discrete latent representation, discrete code. For example, it's maybe more efficient to store, in usual Gaussian variational autoencoder, you have these float numbers that first might be slow to work with because they require like final floating coprocessor. Maybe these operations are slow on modern CPUs, and then not all the digits, not all the bytes, not all the bits of this representation are equally important. You can assume that if you take your usual float, those some last bits might be unimportant because they contribute only very small addends to the resulting value. So you waste your space for nothing. Whereas here in the discrete case, all the variables are used equally well. Well, never mind. Just for some reason you want to have discrete code. Let's not dig into the motivation. So yeah, this is our discrete code that has some prior probability p, and our observations are also discrete because in this case I'll be doing modeling of monist random digits. We approximate the posterior with this factorized Bernoulli distribution. That's just to say that you have an encoder that generates your stochastic binary code. It just generates means of these values. And the objective is the usual evidence level bound. What's important here is that I have computed the Kyle divergence between the code and the prior analytically because, for example, I wanted to compare all the methods with the asymptotic reparameterization, and it does not work. You can't relax the Kyle divergence using this reparameterization. This is one of the downsides. It only works when you can invoke the CLT. This is actually why Michael in private discussion objected, because he says that in practice when people are using Gumbel softmax relaxation, they also relax the Kyle term so that the elbow will not be an elbow of your marginal likelihood in a discrete model, but still somehow it works better than if you don't relax the Kyle. I don't know why.
Wait, which one works better?
If you don't compute the Kyle divergence, you can't just compute Kyle between the discrete prior and the continuous relaxation.
Right.
You will need to
So that's
either
prior as well.
you can rewrite it as an expectation and then relax the expectation, but then that would not correspond to any meaningful evidence lower bound at all, because your Kyle will be something strange. Instead, what you do is that you relax the prior also, and that essentially means that you consider a different model, the relaxed model, that you hope that this whole model is close to your original one. For the evaluation, in order to estimate the marginal likelihood, I used the multi-sample importance value lower bound that looks like this. That was proposed by Duraborda. So I think that it approximates, I hope that it approximates marginal likelihood reasonably well, but as far as I know, there is no way to actually check that.
Why not?
Well, I
Since it
mean,
can be proven that in the limit.
in
when
the
all
limit,
goes to
yeah, but
infinity,
is 10,000 enough, or should I use 100 or 1 million?
it's quite easy to check.
What is key?
If your estimate has stabilized, this means that you're almost converged.
But it never does.
Really?
Well,
Have you checked it?
I sampled 100, 1,000, and 10,000, and it was increasing.
As it should be, right? But it should stabilize somewhere.
Well, I don't know, maybe I should have sampled like 50,000, 100,000. I just didn't have a computational budget for that.
What is key?
Kappa is your encoder's mean encoder outputs. Or you mean the small k? Kappa or small k? Well, you see, Bernoulli random variables are parameterized by their mean. So kappa is just what your encoder generates. It's like mu in variational autoencoders. And k is just index. The capital K is number of hidden, is the dimensionality of your latent code.
And I think that index k in the last line is just a misprint. Should be the
Yeah.
L capital or just no index.
Yeah. Well, you can think of it as of, that should be L capital, but you can think of, well, okay, that should be, I can come up with a justification. Okay, let's see some plots. So these are evidence level bounds for training. At the training stage, I computed evidence level bound for both relaxed and discrete elbow on the same mini batch. And you can see that, for example, if you use Gumbel softmax relaxation with temperature equal to 1, then your relaxed model learns very well, actually better than any other, but at some point it starts to overfit. The reason to that is that, well, okay, I haven't checked that, but I believe that if you use temperature equal to 1, your distribution actually looks like this. So it prefers those values in the middle to values on the edges, on the boundary. And the network adapts to these intermediate values. Then what's also interesting is that if you decrease the temperature to 0.4, then the relaxation works. The relaxation does not achieve such high values of elbow, but on the in the discrete case, it actually overperforms all other relaxations.
And you understand right that the plots to the left are not comparable with each other.
Yeah, of course.
So we can't say that the green curve is better than the
I mean, well,
violet curve.
no, I think they are. I mean, they all are lower bounds on the same thing. On it. Well,
I'm not sure. The relaxations are different. They are lower
yes.
bound to some
Yeah, yeah.
relaxations. And since these are different relaxations, the true value of log of incomplete log likelihood will be different. And
Yeah,
this
yeah,
means
yeah.
that we can conclude that the green is good, the violet or cyan is.
Well, okay. The only thing that really matters is the dynamics. That the
Dynamics is positive, good,
green-
but not for the green curve, for the discrete case. And what's important is we know why.
Yeah. Okay, let's see the discrete case then. Well, you can see that if we use different random variable in order to generate our relaxations, replace, recall that earlier I said that it's not clear which x you should be using here, like which x to choose. You could choose Gaussian one, and that's what I did. That's this yellow line. It uses the Gaussian distribution with a temperature 0.4. And well, probably if you adjust the temperature accordingly, there is no reason to believe that the same temperature will work for different distributions. Maybe then you can have the same performance as the blue line.
What is logistic relaxation? What's the difference
This is
between
just the
logistic and
Gumbel
Gaussian?
softmax. Logistic is a special case of Gumbel in a binary case.
So does it
here
mean
also-
that the choice of continuous random value really matters?
Well,
You
actually,
compare to relaxations with the same temperature.
yeah,
I
but
think
it's
I'm
not
not
clear
over-
whether you should use the same temperature. Probably temperature depends on your distribution. However, there is an interesting.
All right.
However, there is an interesting thing to notice. Namely, if you consider the gap between the discrete elbow and the relaxed one, the relaxation gap, you can see the following picture. What's interesting is that for logistic distribution, for the Gumbel softmax with tau 0.4, this gap is kind of constant all the time, whereas for other relaxation, not counting the straight through because they don't relax the forward pass at all. For other relaxations, this gap increases. That's an interesting observation.
So in the concrete distribution paper, there is a theorem which says that in binary case, there are no modes in the interior of 0-1 range. So the situation you showed when the temperature is lower than 1. For temperature 1, it is exactly like the lowest temperature where you can observe modes in the interior of this range. So this is why you're seeing this gap.
Uh-huh.
So it's like you can't prove this mathematically. You should choose the temperature that is at least a bit lower than 1.
Yeah.
Right.
And this is good because we now understand the behavior of the green curve.
Yeah, and the paper, as far as I remember, has this condition for the general k-variate case. Like the temperature should be less than 1 over k minus 1, as far as I remember. So this gives you some guidance on how to choose the temperature in general case, k-variate. Okay, so this plot shows that there is some interesting gap, and actually it shows that the asymptotic reparameterization I was talking about also does not seem to be superior to other methods. Probably because it has this bias of having an approximation, like relying on the central limit theorem when it's not a limiting case. And finally, if you look at the elbows, they basically at the estimations of marginal likelihood, then you basically see the same picture as with the discrete elbows, the same dynamics.
Is it discrete elbow or relaxed elbow?
Discrete, of course.
Ah, of course. So this just confirms that Google softmax is the best method, right? With correctly chosen temperature.
Well,
This is
the
strictly less than
comparison
1.
was not very thorough. Maybe if you look for other values of temperature, maybe you can show that they all perform reasonably well, provided you can choose the temperature. I mean, there is no reason to believe that the same temperature should work for all distributions.
Yes, but there are reasons to believe that the temperature should be below 1.
Well, okay, if I guess
Mathematics at all.
maybe if I but the Gaussian distribution also had the same temperature. I mean, I only showed this case in order to show that choosing the temperature is important. But if I took here 0.04, then probably the Gaussian case would work better than the Google one.
Why?
Because that would be better approximation to the discrete case.
Why?
Well, because in the
Can you please-
limit of zero temperature, you perfectly have.
Nah. Yes, but it's not clear whether we'll be able to optimize it at such low temperature.
I think that's reasonably high.
0.004? Who knows? So that's anyway, that's not evident. That should be checked. Okay.
So that's it. The next thing I have is the fix and reinforce chapter. I'm not sure whether we have time to go through it right now.
It depends on you. How much time will it take you to go through?
Well,
Because I do not want to be in a hurry. It's better to postpone it and to continue next week.
there are like I guess half an hour worth.
Our next speaker is Alexei. Alexei, how do you think?
Wait, right?
Will it be possible? Because you mentioned that you have two small talks, right?
Yeah, we can split it too. We can split in two talks, or we can choose one of them
For example.
after it, and yeah.
So anyway, I think that next time we'll have enough time.
Okay. Well, thank you,
So then-
and come back next week in order to actually what I have in the very end is a very interesting paper.
There are
called-
many interesting things.
called
Yep.
rebar, and this one essentially computes all the coolness of Google softmax with unbiasedness. It makes Google softmax unbiased. What's cool about it is that it's the only okay, that's one of several methods that actually use the gradient information of f. And I believe that this is beneficial for optimization. So I'll show you how to derive it.
And I do confirm the optimism of Artem. So rebar is really very cool tool, at least from mathematical point of view. I'm not sure whether it's really beneficial in practice, but in theory, it's cool.
So far I haven't seen any papers using that, but I believe those are to come. And yeah, I give you a conclusion even though we haven't finished all the slides. There were many and will be some more techniques to backpropagate through stochastic nodes. I actually haven't covered all of them that you heard of. More are in my blog. I have so far posted only first part of a series of 3 posts. I almost completed the second one. I guess I'll publish it today or tomorrow. And the third part, discussing the third chapter of NVIL, beam core, rebar, and fix and reinforce in general, will follow, I guess, next weekend. So subscribe to my blog, and you can find the implementations of discrete variational autoencoder here. They are still work in progress, so be careful. The repository can be broken when you check out, because I use it to sync with the dev server. Okay, that's it. Thank you.
Any questions to the speaker? Okay, all questions have been asked during the talk. So, thank you. So we'll continue in a week, and our next speaker will be Alexey Umnov, who will give a talk about some of his thoughts about generative adversarial networks.